So folks, in our last video we built the simple harmonic oscillator model that we're going to utilize in analyzing these springs. So let's go ahead and put that into an example. I want to point out in the example below I usually pick numbers that are easy to work with, and so that makes the situation maybe a little bit less realistic, but if you used, instead of a spring coefficient of 4, maybe you use 0.5 or something like that, it'll be a more realistic model, but it just means that the calculations are a little bit harder to do, and I'd rather focus on working through the problem than getting bogged down in working with small decimals and such. So here in this problem, suppose we have a mass of 2 kilograms, so we're told explicitly that the mass is 2 kilograms, and when this suspended from a spring of negligible weight, it stretches that spring. When the mass is hung from the spring, the mass stretches 5 meters from its equilibrium point. We're going to use this information to find K. What was K? Remember that K was that spring constant. We're going to use that information to help us find K along with the mass of that object. When we affix one end of the spring to the wall, so the spring mass system may oscillate left and right, and we suppose that there's a dampening force. What's that dampening force? That dampening force is some sort of drag coefficient here, or there's some sort of drag force, and it will have a drag coefficient with it, and we're told that it is 6 times the object's velocity. So that's going to allow us to find so this is to help us find the B value that we use for our drag, and again this was for our mass. Okay. And then finally, we suppose there's no external force on this problem. In later problems we'll start putting in a external force that'll make the nth order ODE no longer homogeneous, and we're learning right now how to work with some of our non-homogeneous cases. And then finally in this we're going to use negative 10 meters per second squared for the acceleration due to gravity. Watch out for that each problem. And I want to reiterate one thing, folks. We're going to work through this. I should have everything worked out in the correct order, but at the end of the day, when it's time to give your spring mass model that looks like this, make sure that each of these quantities are positive. And if one of them came out to be negative, you go back and you see where you made your sign error earlier. But these should all come out to be positive values when we've written the second order system this way. This is for a real world spring, I guess I should say, for springs that behave the way they do in our world. Those should all be positive. Okay, so let's go ahead and give the differential equation for this spring mass system. We'll give the solution to it, and then I'm going to go ahead and give you an initial condition, or pair of initial conditions to allow you to solve this. Okay, so we're trying to build what? We're trying to build this model mx double dot plus bx dot plus kx equals f of t. That's what we're trying to build here. Okay. So here we already know m is equal to, we said that the mass was equal to 2 kilograms. Now folks, sometimes I might give you the weight of this object, and then you'll have to find out what its mass is based on converting from weight to mass. So watch out for that sometimes. We're told that the drag coefficient is actually 6. We're told B equals 6 explicitly in this problem. And we're told that f of t is equal to 0. Generally, folks, I will give you an easy way to compute the mass, or I'll give you the mass explicitly. I'll always state if there's a forcing function or not. This will usually just be a value. We could experimentally come up with what our drag coefficient is, but generally I'll just go ahead and state it to you. What I will often have you find is I'll give you enough information to figure out what your K value is in the spring. So let's go look at what we were given here. We were told that if we were to hang this mass, well, first of all, if we just hung the spring right here, this is where the spring wants to rest. So this is called the equilibrium position. Okay. That's where the spring wants to hang normally. And then what we're going to do is we're going to affix a mass to it, and that's going to cause the spring to stretch. So there's our mass, and specifically that's a mass of 2 kilograms in this case. And when we hang that mass to it, it stretches this a distance of 5 meters. So again, folks, 5 meters is a lot. I chose these numbers so that the the characteristic equation factors and factors nicely. So this is a little bit contrived, but it gets the same point across. So we're not having to deal with messy decimals as we work through this. Okay, so right here, we notice that when I hang this mass of 2 kilograms and it stretches at 5 meters, the system will be at rest if we let it just hang there. And so when a system's at rest, we know that the summation of all the forces has to equal 0, meaning there's no acceleration. But what are the 2 forces on this system right now? So this is not later on when we stretch the spring and release it. This is just as it's hanging here from the ceiling. What are the 2 forces on it? Well, there's a force due to gravity, and there's the restorative force. So we've got mg minus kx has to equal 0. That's the sum of the 2 forces. Remember that the restorative force is always as a negative kx. And that has to equal 0 in this case if this is just hanging here. Okay, so our mass was 2 kilograms. We were told that. We were told to use minus 10 for our acceleration due to gravity. There's the minus k, and that's what we don't yet know. And the amount that we've stretched this is 5 meters downwards. And since our acceleration due to gravity is downwards and we wrote it as minus 10, we're going to orient this so that this is minus 5. So I should have changed that to a minus 5. Watch out there, folks. So that should be a minus 5. And that's just how I chose to set this up. If I was using positive 10 meters per second squared for the acceleration due to gravity, and I was thinking of downwards as positive, then I would count this as positive 5, and I would have to adjust these 2 values accordingly. Remember, folks, if ever you get to your system that you're trying to build, this mx double dot plus bx dot plus kx plus your forcing function, or is equal to your forcing function, make sure that these coefficients come out to have the correct sign. Okay, so this would give me minus 20 plus 5k is equal to 0, and I'm able to solve now for k, and we get that k is equal to 4. So now we can give the model in its entirety. So here's our model here, and this was part A of this problem, was to give the model. So part A, here's the model in its entirety. It'd be 2x double dot plus 6x dot plus 4x is equal to 0. And that's where we found the mass because we were given the mass. We had the drag coefficient, which we were given as b, and we just solved for k. Notice, folks, at this point all coefficients here are positive. That fits with this being a real-world spring problem. Okay. All right. So that was part A. For part B, we want to go ahead and solve this ODE. So to do that, we need to give the characteristic equation. Remember, folks, at this point I'm just jumping straight to the characteristic equation because I've solved enough of these to be able to do so. But if you're not sure where this characteristic equation comes from, make sure you go back to some of those earlier pre-works or in-class notes where we were more careful to write it all out. If I divide everything in here through by 2, we get r squared plus 3r plus 1 is equal to 0. And in this case, we get 2 roots to the characteristic equation. They are both real and they are distinct. So although we haven't yet said exactly why we can do this, we're kind of building this up. We know that our x of t can be written as a general solution as c1 e to the minus 2t plus c2 e to the minus t. What I want to point out here, folks, is although we've got this, and this was for this spring mass system set up, I think we said initially we hung it from the ceiling just to be able to compute the k value, but then we thought of this spring mass system as, you know, here's our equilibrium position, and we've got our mass. Maybe it's on rollers to kind of simulate how it would oscillate back and forth, and we've got our spring that's going to oscillate, the spring mass system that we're going to oscillate back and forth. But in this case, folks, because our drag coefficient was so high, in this case it was 6 times the amount, notice that when I went through to solve this, I got real roots to the characteristic equation. And so we just have these 2 exponential terms in our general solution. Who's missing from this that you might have expected? We're missing a sine expression or a cosine expression, meaning there's going to be no oscillation about this point, and instead this drag force is so high, you could imagine maybe this is sitting inside of a very, maybe we've got, like, this is sitting inside of a tank here filled with really thick oil. And so when we release it, although it's going to restore to equilibrium, it's not going to oscillate back and forth about that equilibrium position as it would if there were sine and cosine values in my solution. Don't worry, you're going to analyze plenty of those cases as well. Okay, so that was part B, was to solve the corresponding ODE, or to give the general solution to it. And then part C is to look at this specific IVP. So let's just go ahead and state the IVP, even though we've already solved the ODE here. So the IVP would be to solve 2x double dot plus 6x dot plus 4x equals 0. This is a second order ODE, and so the IVP is going to have two initial conditions. We're told that the spring is initially stretched 2 meters, and I should have said, it says 2 meters, I should have said 2 meters to the right. Let me make sure that's what I did in my notes. Yeah, this should be 2 meters to the right, and so then x of 0 we know is 2. So in this problem, we've stretched before we release it, we stretch it 2 meters to the right, and then we release it. And we're told that it's, careful, here's our second initial condition, so that was the first one here. There's our first one. Here's our second initial condition, that it's released from rest. That's telling us that x dot at time equals 0 is 0 because it was released from rest, as opposed to being released with a velocity already put into it. So there are our two initial conditions. And we've already solved this ODE. We solved it in part B, and so here was our solution, that x of t was equal to c1 e to the minus 2t plus c2 e to the minus t. And so we just need to figure out the particular solution for this IVP. Notice that because this coefficient function here is just 2, and so never 0, and all of the other coefficient functions are everywhere continuous, that we do get a unique solution to this. So we are going to get a unique solution to this IVP. We go ahead and take the plug in our first initial condition, so we know that x of 0 equals 2. That would imply that 2 is equal to c1 e to the minus 2 times 0 plus c2 e to the minus 0. So that gives me 2 is equal to c1 plus c2. Let's hold on to that equation for just a second. Then if I were to take the derivative of our ODE, our solution to the ODE, if we were to take the derivative to our general solution, we would get negative 2c1 e to the minus 2t minus c2 e to the minus t. And then if we plug in the initial condition that this was released from rest, that would tell us that 0 is equal to minus 2c1 e to the minus 2 times 0 minus c2 e to the minus 0. And if we go ahead and clean that up, we get 0 is equal to minus 2c1 minus c2. So that's our second equation. So now we've got this system of equations that we'll have to solve. So here are the two equations. c1 plus c2 is equal to 2, and minus 2c1 minus c2 is equal to 0. Lots of ways we could do this. I could set up a matrix. I could set up the matrix 1, 1, minus 2, minus 1. That's the matrix of coefficients, and we adjoin it with the right-hand side there, and we could run through the row reduction algorithm. I guess since I've started that, let's go ahead and do it that way. In this case, it might have been easier to just go ahead and add the two rows together to eliminate a variable and proceed from there. But lots of ways we could do this. And I want to just double check here, folks, make sure I don't have an error. We're looking good. Okay. So we've already got a 1 in this pivot position, so let's copy it down and let's get zeros below it. So if I multiply this row by positive 2 and add down, and that's in REF form. I could go ahead, it's not looking too hard to finish it out, so let's finish it out putting it fully into our REF form, so we'll get a 0 above this pivot one. So if I multiply this row by negative 1 and add up, we get 1, 0, minus 2. And so that tells us that C2 is equal to 4 and C1 is equal to minus 2. Of course, folks, you can solve these systems of equations however you like, and now you have a whole collection of methods for doing so. You can use your algebra techniques. That's probably what I would have done with this one, because it's clear that if I add these two equations together, the C2s will add out. You can use your matrix row reduction. You could compute the inverse of this matrix, and it will exist because of the existence uniqueness theorem. You can compute the inverse of this matrix. You could use Cramer's rule. So you've got lots of methods for solving this, and we went ahead and found the two coefficient values. So at long last, we're able to give our solution to the IVP. So x of t equals minus 2e to the minus 2t minus 4e to the minus t solves our IVP. Okay. Folks, we'll pick it up in the next video. I hope this was helpful and a little bit interesting.